All right, line A4, learning task 4, we're going to take a look at solving some of our series RLC circuit problems. So the previous 3 learning tasks were just dealing with the theory of how we add together, the different values of voltage and inductance, reactance, capacitance, all that other stuff inside of a circuit. Now we're going to go and start putting them into larger videos. What I am going to do is I'm going to work through each of the problems. Now, in some cases, it might be different than what the book is doing. The book is going to go and show you one method, which is going to be, using in a lot of cases Pythagoras or sometimes sine and cosine, and I'm going to rely a lot more heavily on the calculator because at the end of the day, what you need to be able to do for completion of level 2 is to be able to solve these, whether you're going to solve them through the book method, which you can then go through self-study that one, or whether you want to be able to utilize this calculator for that one. That's up to you as well. So don't expect them to be the exact same. Sometimes what they're doing is going to be different, but we're going to get to the same result. Or if we're at a different result, I'm going to explain why and if we've got any sort of errors that are inside of the book that have been propagated. We know there's been some errors inside of here. Excuse me. So don't freak out if all of a sudden there are more errors inside of here. That's what this is for, is to correct stuff. Okay, let's start with the very first one that they have over here. Now, the very first one that they give us is this circuit over here, where we have got a watt meter inside of there, which we should recognize is going to be measuring true power measured in watts. I'll be able to pull that right off of there. And then I've got a inductor, or a reactor, and we know that a reactor is going to be made up of copper wire, which is going to possess resistance, as well as it's got the turns, n squared mu a all over top of little l, which is going to go and give us our inductance. However, they're inseparable from each other. It's absolutely impossible for us to separate, the physical from the electromagnetic inside of there, which means that we treat them as a whole unit, but we know that inside of there, there's different components doing different things. What we want to go and do inside of here is we want to know what's my value of resistance. We want to know what's my value of XL inside of here. We want to know what is my value of Z inside of this circuit. And we want to know what is my figure of merit, or my Q, of that coil. All of these need to be solved out of there. So let's start with what we are given. First of all, we are given 75 watts, so we can place that right away into a power triangle. Do we like power triangles? Absolutely, because power does not lie to us. What other values do we have inside of here? Well, if we take a look, we see we've got 5 amps that is going through each of these components. It's a series circuit over here. Okay, disregard this line. This is just the watt meter. It's voltage section. For those of you that are unfamiliar with the watt meter, it's got a voltage section. That's a voltmeter inside of there. And it's got an ammeter section. That's an ammeter. That's inside of there. So don't worry about that line there. That's connection for the metering. We see that there's 5 amps that's flowing in series through these. I also see that I'm dropping the full source voltage over top of it. This needs to be, right, Kirchhoff's law of voltage, the sum of all voltage drops is equal to my source voltage. So therefore, we must be dropping that 125 volts over top of it. Well, if I have got my line volts and my line current, I can use those two together to go and establish my VA. Let's do that. 125 multiplied by 5, 125 times 5, gets me out to a value of 625. 625 VA. We'll add that onto our power triangle. So our power triangle, I'm going to have to move this thing down because obviously 75 and then 625 is going to be way, way larger. 625 VA is going to look like that. At this point, what can we go and solve out of here? Well, we can go and figure out our impedance off of here. Once we know what our impedance value is, we can then go and work off of our resistance of our coil to go and figure that out off of our watts, right? We know that we have got this 5 amps that is transferring through here. Therefore, we know that we should be able to use either my E squared over R or my I squared R to go and figure that out. We aren't looking for values of voltage inside of here. We're looking for the impedance values of this one because we're going to take this inductor and we're going to move it into another circuit in a minute. Let's start by figuring out what we have got for our resistance off of this one. R is equal to I squared divided by W that we are going to go and have. Oops, sorry, upside down. W divided by I squared. I'm working off the wrong one. I should do the W is equal to I squared R. What we're going to isolate for is we're going to isolate for the R, so we're going to go and divide the I squared across to this side. Moves it out of that side. So we have R is equal to my watts divided by I squared. What's my watts? 75. What's my I squared? I squared. I is 5, so 5 squared. 5 squared is equal to a value of 25. So 75 over 25 tells you that my resistance value has to be a total of 3 ohms that I'm going to go and see. Let's put that inside of here as a solved value. 3 ohms like that. What's my impedance? Well, my impedance, R is equal to E over top of I. And if I'm looking at a whole circuit, we know that instead of R, we have impedance. Z is equal to my E over I. If I take 125 volts as my E value, 125, and if I take 5 as my I value, we can just go and divide that across there, and we're going to come out to a total impedance of 25. So my Z is going to be 25 ohms Z. We're going to stick that little subscript on there. Perfect. We can start to go and build out a triangle for that one then as well. It's going to be a similar sort of triangle. 3 and 25 ohms Z, and this is going to be 3 ohms of pure ohmic value resistance. Last thing that we need to go and find then is going to be my XL. Now, if I take a look at these, I don't have any phase angles for these ones. I don't have any way that I can punch the calculator in off of them, so we are going to have to use Pythagoras for them. You can either work off of the 625 and 75 and create your total bars and then work backwards from the bars, but that seems like a lot more work than what we need. We might as well just go straight to this one over here and work off of my impedance minus my resistance. Formula for that one is just going to go and be that this side over here, XL, is equal to my root of Z squared minus my R squared. We take the square root of that entire thing. My total Z is going to be 25. My total R is going to go and be 3. So I'm just going to go and put those, square them into there, and then subtract and take out my XL. Second root, bracket, 25 squared minus 3 squared, bracket, equals 24.82 that we would have for that. They're rounding inside of the book to 24.8, so we will just go and do the same as well. 24.8 ohms XL. This one over here, 24.8 ohms XL. Last thing that we have is going to be my figure of merit. My figure of merit is basically how inductive is this coil compared to how resistive, and it's just going to be a matter of taking my XL over top of R. So 24.8 divided by 3. Punch that into your calculator. We've still got it stored inside of here, so let's do divide by 3 equals a value of 8.27, or they round that one up to 8.3. 8.3. Note that there's no units for the Q. It's simply just a ratio. It's got a Q of 8.3. Perfect. That's our first one. Now what we're going to do is we're going to go and take this coil, which we've placed across here. We've taken a watt meter, and we have taken measurements, amps and volts, and we've figured out what our Q is, etc. Now that we know what that coil is, we can go and take that coil and we'll move it into another circuit. The next circuit that we're going to take a look at is going to be this one over here. Now let's go and just transfer some values that we have from the other one. First of all, the physical resistance is not going to go and change, right? It's based on K times L over top of CMA. So in this circuit over here, we are going to go and have the same 3 ohms that are going to be crossing. Secondly, my XL of 24.8 is going to go and stay the same because XL, as long as my frequency is the same, I see 60 hertz there, and I see 60 hertz there, we know that XL is equal to 2 pi FL, and if my frequency stays the same, if it's the same coil, the same L, my XL will be the same as well. So we'll drop that one in over here as well, 24.8 ohms XL. And then we're now going to go and add that into a 40 ohms onto this one. Now what we're going to do is we are going to go and look for my total circuit resistance, my total circuit impedance, my effective current, the power taken by the resistor, the power taken by the coil, the total power of the entire circuit, the VA of the total circuit, the power factor of the coil. Then I'm going to look at my phase angle. And then I'm going to go and look at the power factor of the entire circuit, and then I'm going to go and take a look at my phase angle of the entire circuit as well. All right, let's step through one bite at a time. The first thing that we should notice is that we've got a need for some sort of consistency inside of our calculations, right? If we don't have something that we can go and treat the same throughout all components, this component, this component, this component, it's going to make it hard for us to go and, differentiate between each of them in our calculations. What is that one thing that we're able to go and keep the same across all of these? Well, the only thing that we can keep the same across all of those, I'm just going to remove that, is going to go and be this value over here, my amperage. So let's go and take our amperage. In order to go and find our amperage, though, what we will also need to have is we are also going to need to know what is my total impedance, right? We know that if we know what our total Z is over here, then we can go and figure out our total I line that we would have as well. So let's start by creating the Z. Now we know that our impedance is going to be the vector sum of all of our values of resistance plus all of our values of reactance. We know that we have got 40 ohms of resistance, plus we have got another 3 ohms of resistance, right, from the coil itself. And then we are going to go and have 24.8 ohms of inductive reactance that we are going to have, which altogether is going to go and get us out to our grand total. We'll make them a little bit shorter so it's a bit more in line with what this thing should be. What we'll do is we're just going to go and add those values together. Once again, if we are taking a look at XLs and if we are taking a look at Rs, we know that resistance is always along the x-axis, and because of this, Eli, that the current leads voltage leads the current for an inductive circuit, and because my current is always in line with my resistance, that means my inductive voltage would be going upwards, which means inductive components, we're always treating those as going upwards. So they're going to be at a positive 90 degrees. Let's go and add these in at positive 90 degrees. We'll identify these ones here. These are going to be at 90. These are going to be at angle 0 and angle 0. So we'll add all of that into our calculator. Let's put ourselves into the proper mode, mode 3, and then we're going to go and put this thing into polar so that we're going to go and get the vector sum, not the x, y coordinates, and we'll add these all in now. 40 angle 0 plus 3 angle 0 plus 24.8 angle 90, it's positive 90, equals a value of 49.64 at a degrees of 29.97. Let's go and put all of these values onto our drawing over here. We'll start by putting in this impedance that we had, and our impedance was this value, 49.64. So 49.64 ohms. Z that we are going to have. We've also, at the same time, because it's a series circuit, we've got this angle off of here, which we can go and do some stuff with as well. First of all, the angle is going to be our phase angle for the entire circuit. It's 29.97. So we'll put that one in there. Theta equals 29.97 degrees that we are going to go and have. And then we're also able to go and take this angular degrees and we're able to convert this thing into a power factor, right? You remember that formula? We'll just write it out. We know that the cosine of our angle is equal to our power factor. So if we take the cosine of 29.97 degrees, that's going to go and give us our circuit power factor as well. We'll go cosine of 29.97, which equals a value of 86.6% that we have for our power factor. So we'll put that one in there as well. Out of room down here, but that's okay. PF equals 86.6%. Now, if you go and work along inside of your binder, you'll note that these values are a slight bit different from what's inside of the binders. By the time that they get to this angular degree, they've gone through a number of other calculations, and so they've had a little bit of rounding error that starts to go and accumulate. Their degrees are going to be 30.4, 30.6, let me find 30.6 degrees is what they are going to say is going to be the phase angle of the circuit. They're going to say that the power factor is going to be, a straight 86% that we are going to go and have over here. That's fine. It's they've done a different methodology to get there, and because they've gone through all those steps, we've just had propagation or carrying over of that error from step to step to step. We don't really want to see that, so we want to go as accurately as possible. Is this accurate what we've just done here? Absolutely. It's the calculator that is doing all the math for us. We're putting it in, angle 0, and then we get that 24.8. And we know that we've got this 49.64 ohms. Really where they started to kind of deviate was they went in with a 49.7 inside of their book that they had rounded out to. So don't worry too much if you're a little bit off from what the book is. I prefer doing this because it gets me to these values here immediately, and after that, once I've got those values, I can start working those things back into other components. Now, what were we en route to go and find? What we were looking for was we were looking for I line, because we didn't know what that I line was, but once we find it, we can then go and figure out watts, and we can go and figure out, bars and VA and all the rest of that stuff off of it as well. Let's go and figure that out now at this point. We've got this ohm Z, which is my total impedance. Remember that my source has got no eyeballs. It can't see what's hooked up to. All it knows is it needs to overcome 49.64 ohms. And in order to go and do that, it's going to have to dump out a certain amount of amps. I is equal to my E over top of R. So we're going to go and place in our total voltage, our source voltage, 250 volts, and our total impedance, which is our opposition to current flow, our resistance of the circuit here, 49.64. And once we've got those two together, we're then able to go and calculate our current. 250 divided by 49.64 equals a value of 5.04 amps that we are going to go and have. We'll round it to 2 decimal places over here. So this 5.04 amps that we are going to have. They rounded here, then they rounded here, and then they carried that through all of these, and that's where they eventually spat out to their angles and their power factor. That's where we're starting to see that error propagate inside of what they did. Okay, let's go and take these values now back into our circuit. What they're going to do is they're going to go and round the 5.04 amps. They hit 5.03, but they're going to go and round this thing out to become 5 amps. And so that 5 amps that they have is then going to allow them to calculate a bunch of other stuff, rather easily, but it's going to lead to, some rounded numbers. In the field, would this make much of a difference? Absolutely not. We're usually an amp or two difference is really about all that we're looking at. We consider that to be line resistance or maybe a slight bump in our voltage or whatever it's going to be. For these calculations as well, when it comes to exam time, as long as during the process you're rounding to 2 decimal places, you're going to be fine. I do allow a little bit of leeway for whether you're going to go, round the circuit in this direction or round the circuit in this direction to get to it. And so there will be a percentage. If you're close enough, you're going to be close enough. All right, let's go back to these ones over here. Now that we have got that current that goes there, we can go and develop a bunch of different things. We could develop the individual voltages across these, but there's no sense in developing the individual voltages across these because we don't actually know what we would have. We can't separate one to the other. So we won't look at these individually. We can develop the voltage seen across this resistor over here because that one we would be able to measure separately. So I'm going to place my amps is equal to 5.04 going through there. Same with these ones over here. Amps is equal to 5.04, right? Because it's going through all these series components. What we can do now is we can work off of Watt's law. Get rid of a bunch of these other calculations that we aren't looking for at this point. And let's go and transfer to our Watt's law that we are going to go and have. Watt's law for this circuit is going to go and tell me that, I squared R is going to be equal to my watts, or I squared XL, or I squared Z. Any one of those is going to get me to my power value, whether that's going to be watts, VA, or bars, respectively. Let's go and work off of this one over here and figure out what we have got for watts. So 5.04 squared multiplied by 40. Gets me to a value of 1,016 that I'm going to go and have for this. So this 1,016 watts. They round theirs down to 1,000 watts because they rounded down their 5.04. We got 1,016 watts over here for this one. What do I have for this section over here? Well, once again, 5.04 squared multiplied by my 3 ohms of resistance. That tells me that that coil is putting off a total of 76.2 watts. And then if I want to go and figure out my VARs that I'm going to go and have inside of this circuit, we can go and do the same thing. 5.04 squared times 24.8. Gets me out to a value of 629 bars that I'm going to go and have off of this one. If I want it, I could take all of these watts values and I could go and add them together into a similar looking triangle as this one here, where I would have 1016 watts plus another 76.2 watts plus my 629 bars. 629 bars. And I know that what I'm going to go and have as the result of that should be my total VA. Well, what is my VA? 5.04 amps multiplied by 250 volts. Let's find out what our total VA was. 5.04 times 250 gets me to a total VA of 1260. So 1260 is what I should have out of this thing. We'll put that VA down here. VA equals 1260 VA going across here. What's beautiful is that all of these other calculations that I did for VARs and the individual watts and stuff like that, I should be able to get the exact same results out of there if I take my total VA at 1260 and if I apply it at the proper angle, right? We calculated that angle earlier off of this one. The angles have to be the same all the way along. So let's go and do so. 1260 at an angle of 29.97 degrees. I'm just going to hit enter, VA or equals, because that stores in memory. Now that's stored in memory, I'm then going to go and hit the convert to XY. And if I take a look at the first value that comes out as my X is a total of 1,091.5, which is going to be my total sum. 1,091.5. That's going to be my total sum watts, my X value. And the second value that comes out of that conversion, if I go comma over, tells me the Y is going to be 629.4, 629 bars. Let's just go take a look at these two, 1,016 plus 76.2. We can just verify that they add up to become that. Gets me to 1,092.2. So a little bit of rounding that we've had inside some of these ones over here, just due to the way that we built our way through. But if I go back to my VA, put it in the power at the angle, I see that I'm able to go and get that total circuit that I would have as well. So we've solved so far most of the stuff that we've been looking at. I'm just going to go back to the very beginning of that example. Let's just go through the chart and let's list off the ones that we have. So starting at A, they asked for total circuit resistance. We didn't actually explicitly solve that, but we said, 40 and 3 together are going to be our resistance. That's 43 ohms of resistance. Total circuit impedance, we have solved that one. That's B. Effective current, that's my I line. That's going to be C over there. True power taken by the resistor, that's going to be this watts that we have over here. True power taken by the coil, that's going to be this watts that we have over there. True power in the entire circuit, that's going to be this value, 1091.5 watts that we have over here. Apparent power, or VA, of the entire circuit, that's going to be this 1260 that we have over here in these two locations. The power factor of the coil, that one we don't have yet at this point. The angle by which the reactor current lags the reactor voltage, that one we don't have as well. That's going to be looking just inside of here. We'll get that one in a minute. Power factor of our entire circuit, absolutely, we have got that. The angle by which the line voltage leads the line current, or in other words, the complete power factor angle of our circuit, that's going to be this 29.97. So really, the very last section that they're asking us about is going to go and be what I've got for my reactor itself, the power factor of the coil and the reactor coil of the coil itself. Well, if I'm only looking at the coil, I should be able to draw another little triangle made up of just these little sections. That's going to describe the coil. It's got the resistance of the coil, and it's got the XL of the coil alone. Therefore, I'm going to be able to go and see the total impedance of the coil, and I'm going to be able to go and see the angle, which is going to be critical because that angle is then going to give us that power factor. Let's go and take a look at that. We'll just add this value and this value together vectorially to go and get that phase angle. First of all, I'm going to go and I put myself back into polar mode. And now we're going to go and take those values. 3 angle 0 plus 24.8 angle 90 is going to go and get me to a value of 24.98. That's going to be my total impedance of that coil at a degrees of 83.1 degrees. This is something that we do need to go and write down because that's our actual phase angle over there, 83.1 degrees for that. And we know that if we take the cosine of our angle, we are then able to go and translate that into our power factor, right? Cos theta equals power factor. So we can just take the cosine of 83.3, cos 83.1 instead of 83.3. Gets me to a power factor of that, just the coil section of 12% that I'm going to go and have. PF of our coil. If you go and carry those ones into the binder, you can go and follow through. We see that these last two values over here, which are the coil values for angular degrees and for a power factor of that one, those work out to what they have inside of there as well. Once again, the entire thing that we have gone and drawn inside of here does work out for what all of our individual values themselves are going to be. It's just going to be a little bit different due to rounding, and because they went through in one order, I went through in another order. Either one will get you close enough to the correct answer that you should be able to, strike that as a correct answer on any exam. The next thing that they ask us to do is to take this circuit that we have over here, and they want us to go and construct a voltage vector diagram for it. And then that voltage vector diagram is going to be used to establish how many volts I'll see across the coil versus how many volts I'm going to go and see across the resistor over here. We know that we've got a grand total of 250 volts. So I'm just going to move over to this next page over here. And we're going to start by establishing, what do we know? Well, we know that ultimately for this circuit to have a voltage vector diagram, the sum of all voltage drops, that's all of this, has to equal my source voltage, which is going to be this value over here, 250 volts that I'm going to go and have. That's where we're going to start for what we're going to go and do. We're going to go and say 250 volts. Now, we don't know exactly what all the other sides are going to be, but we do know the total angle of that triangle, right? Because we calculated that inside of here. We calculated that thing as being 29.97, which means that now that we know that that's at 29.97, all of our triangles have to be the same inside of here. So we can go and punch that in off of this one over here. They have 30.6. That was their rounded error. We're going to go and put in our 29.97. We're going to finish solving this thing with the values that we have. So I'm going to go and take, we're inside of polar mode over here, R theta. So I'm going to go and take 250 angle 29.97, which equals a value. So I stored it in memory by hand that equals, and then I'm going to do that conversion to my XY. My X value is going to be 216.57. We'll round that to 216.6. So let's place that on here. 216.6 volts, and that's going to be all the way across from here to here. And I know that my Y value is going to be 124.9. 124.9 volts that I'm going to go and have. This is going to be my inductive voltage. Now, we know that we can't separate the actual inductive voltage out of our inductor, right? They're one complete unit, so there is an inductive voltage drop, but we don't really know how to go and pull that thing out. There's no way to measure it separately. What we do know is that we can go and establish the number of volts that I'm going to go and have over top of my watt meter, and once I've got that inside of there, I can go and find the difference, what I'm going to go and have left across here. Let's go back to this watt meter over here. V is equal to I times R, right? Straight up Ohm's law. So if I've got 5.04 ohms, I can go multiply that by, or 5.04 amps, I can multiply that by 40 ohms over here. 5.04 times 40 gets me to a value of 201.6 that I'm going to go and have. So we'll carry that to this one over here, 201.6. I know that across just the resistive section, I'm going to be dropping 201.6 volts, which leaves me with the difference that I'm going to go and have over here, right? If I've got 216.6 minus 201.6, that tells me that I should have a value of 15 volts that I'm going to have over here. That's good, because now that we've got that, we know what our individual resistive section should be, right? The resistive section should be 15 volts. We know what our XL section is going to go and be. Oops, sorry. That's going to be this 124.9. So we should be able to go and establish what the total net sum would go and be going across this coil over here. We don't know what that is at this point, but we can punch that into our calculator. 15 angle 0 plus 124.9 angle 90 equals a value of 15. Now it's still in XY, so it's just spitting back the same values that we have over here. So what we're going to do is we're going to do a conversion. Gives me a total VA of 125.8 at an angle of 83.1. That's what we're looking for over here, 125.8 at an angle of 83.1 degrees over here. If I go back to this circuit over here, if I were to go and throw a voltmeter across this inductor, when it's operating, I would be measuring that value of volts. V is equal to 125 volts that I would have all the way across from one end to the other, because I cannot separate out the resistive and the inductive sections. They're just intertwined. It's going to be impossible. What's kind of cool over here as well is that we solve through it like this by going and taking these ones here and adding them together. There is an alternative method. The alternative method is that if I know that the sum of all voltage drops is equal to my source voltage, right, Vs equals my VR plus my VL, the voltage dropped over top of the inductor, the voltage dropped over top of the resistor is equal to my source voltage. Why could I not then say, if I subtract my VR, so Vs minus VR is going to be equal to my VL. Absolutely. All we have to do is we have to do vectorial subtraction. It's possible, vectorial subtraction. All I need to do is I need to go and take each of these at their angles, 29.97, and this one over here at its angle of 0 degrees, and I'm able to go and spit out this exact same answer over here. Let's just do that one really quickly. If I go back to this one here, it's going to be 250 angle 29.97 minus my voltage that I have across here, which is 201.6. 1.6 angle 0. So we're going to take our source, subtract out our VR, gets me to a value of 125.78, 125.8, that'd be the same as what we have over there, at an angle of 83.1 degrees. It's a wonderful, wonderful thing how this calculator spits out all of those values for us. All right, that gets us through our very first 3 steps. It gets us all the way up to here. They do show an alternative way to go and draw these ones out over here using a scale and centimeters and things like that. We're not going to go and use that scale in the centimeters because we got the handy dandy Sharp calculator, which basically does all the work for us. But they go through this thing and why those angles are adding together. I'm not going to go and bother drawing through all of those though, because it's just far, far simpler for us to go and use what's given to us inside of that calculator. At this point now, we've got the entire thing solved up. We solved that inside of step 2, that voltage. All the rest of the yellow highlights were solved inside of step 1. We solved that one inside of step 2 as well. That was that 201.6 volts that we had. Lovely. We're going to stop this video here, and then we are going to go and start the next sets on our next video.